Hi, in this video we'll discuss convolution, including the law of total probability for random variables and how to compute the distribution of sums of random variables. So as a recap, the law of total probability says that if x and y are discrete random variables, the probability that x has value little x can be written as summing over all possible values of y of probability of x and y. Using the chain rule, the inside becomes p of x given y times the probability of y having a particular value little y. The continuous case is very similar. You just replace the sum with an integral and replace the probability with a density. In the mixed case, there are more than two random variables. You can figure it out. Okay, suppose the amount of gold that a company can mine is X tons per year in country A and Y tons per year in country B, independently, and you have some distribution to model each. So what is the distribution of the total amount of gold you can mine, which is Z, or X plus Y? So let's start with a simpler case. So let's say X and Y are independent rolls of a fair four-sided dice. What is the PMF of Z, which is X plus Y? So again, the range of Z is from 2 to 8 because the smallest value is 1 plus 1, the largest value is 4 plus 4. So we're interested in the probability mass function of Z. Probability of Z has a particular value little z. So what are the possible ways in which you could get a sum of 6, for example? Well, if x is 1, y has to be 5, but that's impossible because it's a four-sided die. If x is 2, y has to be 4. If x is 3, y has to be 3, and if x is 4, y has to be 2. So those are the possibilities. So in general, you could sum over all possible values of x of the probability of x having value little x and y having value little z minus little x. Y has to have that value in order to make the sum little z. So because x and y are independent, you can split this up into the product of these two terms and apply the definition of PMF. So you get the probability that x has value little x times the probability that y has value little z minus little x. Okay, let's do the continuous case now. This time we need to work with CDFs because densities are not probabilities. So we're interested in the CDF of z, so that's the probability that z is less than or equal to some value little z. Because z is x plus y, plug that in. And we can use a law of total probability to integrate over all possible values of x of the probability of x plus y being less than or equal to z given the value of little x times the density of x there. And because we're conditioning on x having a particular value, let's plug that value in, little x here. And now move y to the left side only, and we have probability that y is less than or equal to little z minus little x. And we can drop the condition on x because y does not depend on x. Okay, and by definition of CDF, now this is just the CDF of y at little z minus little x. So there, that's the CDF of z. To get the PDF of z, just take the derivative. So the only thing that changes is that the CDF of y becomes the PDF of y here. That's it. Okay, so that's a summary of what we talked about. Okay, let's do an example of continuous convolutions now. So let's say x and y are ID continuous uniform 0, 1 random variables. So what is the density of z, which is x plus y? First of all, the range of z is from 0 to 2 because you're summing up random variables that are between 0 and 1. Okay, so if, again, this is a uniform PDF, and the PDF of z is just summing or integrating over all possible values of x between 0 and 1 of the density of x times the density of y at value little z minus little x. And because the density of x is 1 everywhere between 0 and 1, so this term is always 1 within this integral range, so we can remove it. So notice that if you want the density of y to be non-zero, we need to make sure that this value inside here, little z minus little x, is between 0 and 1. So, okay, if z is in the range 0, 1, we already have that z is at most 1, so therefore z minus x is at most 1 too, because you're only subtracting and making it smaller. But also, z minus x must be at least 0 if you want the density to be non-zero. That means that x is less than or equal to z. So the only place where the density is non-zero is in the range where x is between 0 and z. So that's this part of the integral here. So if we plug in the density, which is 1 here, and solve the integral, we just get z. Okay, if z is in the range from 1 to 2, we already know that z minus x is clearly at least 0 because z is at least 1, and x can be no more than 1. So the density is non-zero here only when z minus x is also at most 1, or equivalently, x is at least z minus 1. So if you break up the integral, we only care about the range in which x is at least z minus 1, which is the right term here. And in this term, the density of y is non-zero, it's 1. So plug that in, and then the final result is 2 minus z. Okay, so in general, this is the final result. So the density function is z in the range 0, 1, and 2 minus z in the range 1 to 2, and 0 otherwise. So it looks like a triangle, which makes sense because there are a lot of ways to get a sum of 1, but only a few ways to get a sum of 2. That's if both x and y are exactly 1. Thank you. So in general, you have to be really careful when you're plugging in PDFs because the bounds can be tricky. Thanks.